Hello and welcome back to my channel and to the ongoing series ConQuiz. Today's is 11 and we have already presented in ConQuiz 9 and 10 concept booster on thermodynamics, basically rapid fire true false questions on first law and second law respectively in 2 episodes. And today we are going to discuss some conceptual short answer type questions, SAQ. And instead of choosing some random arbitrary questions and answering them, I have classified my topics into a few categories so that it can be more systematic, not only just going through the questions but also having some outline or map of the concepts, right? So that's why the categories are like this: understanding the state functions through classification, a few words on equilibrium, what's wrong if at all there is any. Often we encounter some concepts which are either misleading or if not wrong completely but incomplete. So it's an art and conceptually demanding also that you have to be very clear that where that wrong point is in the statement or in the deduction. Often we miss that, so we will demonstrate. Assumptions, approximations and conventions, that is very important in understanding physical chemistry. Second law, we have so many statements of second law, at least we will try to understand 2 of them which are very important through diagrams, and a little bit of statistical entropy, and finally a single equation. Sometimes it gives a lot of information and we miss that. So these are the categories under which I will be discussing today's session. So first of all, understanding the state functions through classification. Okay. So now I'll be through question and answers. So after every question, I request you to give pause, think over, and then run it again to get the answer. So for example, P, V, T, U, H, G, so many state functions are there, are classified as in 2 groups, P, V, T in one group, U, H, G in the other. So the question is that what is the basis on which I have, or one can classify like this, P, V, T and U, H, G. So at this moment you try to give a pause, think of it, and let us get the answer. All are energy terms of the second group. So that gives an idea of what state functions, which one is which. U, H, G are all energy and P, V, T is not. Okay. So similarly, here U, T, S, G, A, V. Now out of these 6 state functions, which one does not belong with the others and why? So maybe there are more than one answers, but at least one answer is this. I think you have got it rightly. Temperature. Why? Because it is intensive and all others are extensive. So here you have an opportunity to explain that what intensive and extensive properties are with some examples. Similarly, next question, HUSGA. Now, which one does not belong with the others and why? Entropy. Yes. Why? Because it does not have unit of energy. You see, all other H, U, G and A all are actually energy terms except S, which is energy by temperature. U, H, S, G, A are classified as US in one group, but H, G, A in the other. So here the dimension or energy, these concepts will not suffice to answer this question. You have to think in a bit different way, a little bit of out of box thinking. And finally, the answer is that U and S we directly get from laws of thermodynamics, first and second law respectively. Whereas H, G and A that we have defined as per our convenience, we often call it auxiliary functions, right? So that is the basis for differentiating like this. Well, the next point, a few words on equilibrium. So two questions are there. The which state function is maximized when an isolated system reaches equilibrium, and the next one, which state function is minimized when a closed system with PV work only is held at constant T and P reaches equilibrium. So obviously the answer in the first case is entropy, that directly comes from second law of thermodynamics, because delta S is greater than or equal to 0 in general for an isolated system, of course. So at equilibrium delta S is 0, that means S has reached its maximum value, and the way we have defined auxiliary function G, it is the answer of the second question, that G is minimized at constant T and P, of course, respectively. Okay. Well, then the next question comes easy, that which state functions determine whether a substance is in phase equilibrium between two phases I and J. So which state functions? And one of the most important term in whole thermodynamics is chemical potential. So in the phases I and J, mu must be same. So mu I and mu J, chemical potential. What is the condition for material equilibrium between phases in a closed system of ice in equilibrium with liquid water? So it's like the previous question actually, that mu of water in solid and mu of water in liquid, these two phases mu must be same. Well, for a closed system with PV work only, give the condition of phase equilibrium. So different phases may be there, and what is the condition? According to the last few questions, actually, that mu I, the ith component, is the same in every phase in which I is present, of course, for each I. So there are J number of phases may be there. So if I, the component I, is there in all the J's, then mu I are all the same for all the J phases for that component, and so on. Okay. Now for a closed system with PV work only, give the equation that gives the condition for reaction equilibrium. So now we are talking about a reaction, right? So what is the equation? Equation is actually mu I equals to 0. Nu I is the stoichiometric coefficient of the ith reactant or product, and mu J is the corresponding chemical potential. It looks like a single sum. Actually, there are two sums, the product side minus the reactant side. So these coefficients are negative for reactant side and positive for product side. So actually that gives you the total change in G, that is delta G, and that delta G must be 0. That is the condition. And just for this application, we have taken a reaction N2 plus 3H2, preparation of ammonia 2NH3. So what is the equation, corresponding equation? So you see that right hand side is mu N2 plus 3. So I have multiplied by 3 the stoichiometric coefficient, and here 2. So 2 ammonia. So product minus reactant should be 0, or the reactant side sum equal to product side sum. So this is the necessary condition. Well, so far we have told a lot of times that delta G must be 0 at constant T and P, of course, and it comes straight from Clausius inequality. But if I say that logically with some arguments, can you show that delta G would be 0 at equilibrium or reversal process? So let us see. G is H minus Ts, that is the way we define. Now delta G is delta H minus T delta S minus S delta T, but T is constant. Now at constant pressure, we know that delta H is equal to the heat change QP at P, and delta S by definition is Q reversible by T. So if we just put delta H is Q and T into delta S, that is T into Q by T, so T and T cancel out, so that gives you Q minus Q, and that is equal to 0. So this is how we can easily apply whatever I have learned so far. Of course, you can get it directly from Clausius inequality. So it's a good exercise for students. Well, we are going to the next point. What's wrong, if any? Okay. So let us see a few demonstration often we encounter in our sessions. So you know that a partial derivative del z del x can always be written just introducing another variable y. So that del z del y into del y del x, right? That always we can write. Fine. Now del z del y also you know that it can be written 1 by its reverse del y del z. So zy becomes yz, and similarly yx becomes xy. So in the denominator del y del z del x del y. Now we bring both the terms partial derivatives on your left, cross multiplication. So you can write del z del x into del y del z into del x del y, and that should be equal to 1. Okay, if we just rearrange in the reverse order, so xy you write first del x del y, then del y del z, and then del z del x. So that should be 1. Okay, and here it should strike your mind that sir, in the very beginning in our classes, teachers have shown a different relation which is known as Euler cyclic or chain relation, and which tells that this is -1. So you are arriving at an awkward situation that 1 equals equal to -1. It's not possible. So where something is wrong. Actually, often we do mistakes here. Subscripts are important. In fact, I have deliberately missed some subscripts in the first reduction, that R. This R. That means in this case, all are the same. R. Something is constant. Okay. But in Euler chain relation, it is not the same. When del x y is z, y z then x, z x then y. So completely these two are different expressions. These two are different expressions, right? Just regarding the subscripts. So there is no problem, no confusion. Well, that is an interesting question. PV is some constant for ideal gas that we know since class 9 or 10. But PV to the power gamma is also constant, and that also corresponds to ideal gas. Now my question is that how at the same time both of them can be true, PV or PV to the power gamma. Now you can say that, okay sir, if gamma is 1 then all are same, but you know that gamma is Cp by Cv and Cp is always greater than Cv, so gamma is always greater than 1 or at best equal to 1 at special cases. So in general, they cannot be true. It seems to be like that. It looks like a paradox or fallacy, but no, they are true, both of them, because we are ignoring in this statement the conditions in which these two statements are relevant. In the first case, PV is constant, it is at constant temperature, an isothermal process. But you know, but PV to the power gamma is constant for, of course, ideal gas, adiabatic change, not isothermal, and reversible change, of course. So no problem is there. Both can be true at the same time. Okay. A perfect gas. Now it's a very beautiful demonstration of a very often or commonly done mistake. Perfect gas whose Cv is supposed to be independent of temperature and is given as 3R, and it expands adiabatically into vacuum, right? So the question is simple. You have to find the final temperature in terms of the initial temperature, of course. So there are two students or two group of students. One group are doing like this. So it's straightforward, very simple for them. It is adiabatic and ideal gas, a perfect gas. So they can apply the PV to the power gamma is constant or TV to the power gamma -1 is constant, the formula. So by that adiabatic relations we call it, T2 by T1 is V by 2V to the power gamma -1. Now Cv is given, so Cp is 4R, and then Cp by Cv is 4 by 3. So gamma -1 is 4 by 3 minus 1, that is 1 by 3. So finally you get T2 equal to T1 by 2 to the power 1 by 3. So this is the final relation for final temperature, okay, in terms of the initial temperature T1. But another group of students, they are following a different path. They are saying that, sir, delta U is Q plus W from first law of thermodynamics. Now Q is 0 because it's adiabatic, and W is also 0 because by definition W is minus P external into delta V, and P external is 0 here because the gas is expanding against vacuum, right? P external is 0. So 0 into dV is 0, so it is 0 plus 0 is 0. So delta U is 0, and delta U for perfect gas is Cv into delta T, and Cv cannot be 0, so delta T must be 0. That means temperatures are same. So of course these two results are not the same. Now the question is, which one is correct? Which group of students is correct? Well, at this juncture, I will request you again to give a pause, try to think, explore the concepts. Something is wrong somewhere because both of them cannot be true at the same time. And the answer is that T2 is T1, this is correct. So you can't find any flaw in the second argument. But in the first case, it is not valid because, simply because the relation you are using, it is strictly for reversible, adiabatic, and for ideal gas. Three conditions have to be mentioned. But here it's adiabatic, perfect gas, but reversible, no. It's again vacuum, expansion against vacuum, how it can be a reversible change. So that's the point. But why these mistakes often encounter? It is because of we the teachers, because in the deduction of this adiabatic relations, we often miss that point, reversible. And even if we mention reversible, we forget to show that in which step of our deduction the reversibility condition is required. Unless reversible, you cannot apply that step in the deduction. Okay. So often we miss that, and students also follow the same path. And I have seen many times, including myself, that we the teachers also do the same mistake sometimes. Okay. So this is very important, I must say. Next, delta U equals to 0, conservation of energy, and delta S greater than equal to 0. Second law of thermodynamics, and the first one is first law of thermodynamics, mathematical versions. Now I say that okay, they are all right, but slightly incomplete. So your task is to complete them. So what exactly you fill in the blank so that the statements are really complete statements. Okay, so think, and the answer is you must mention isolated system. So delta equal to 0 for an isolated system, and delta is greater than equal to 0 again for isolated system, or you can say over the whole universe, right? So unless you mention, it's incomplete. Well, this is another tricky question. Spontaneity criteria, right? And we know from second law that delta is greater than 0, of course, for isolated system. And du S V, that means that constant S and V, and dH S and P greater than 0. These are again from Clausius inequality condition for spontaneity. Now both are criteria for spontaneity. The question is, don't they contradict each other? So first of all, it is very important to understand the question itself, right? This is valid for any question actually, but here it's even more. So you have to understand that how it looks that it is going to contradict each other, and then you can go to the answer. How? The first part, that here S is constant in both the cases, in these two conditions. So whatever the condition is, you are putting S constant, okay, and still you are getting a condition for spontaneity. But S, how it can be constant? It should be greater than 0. So at the same time, you cannot say something is constant and something is increasing, right? You cannot say. So something somewhere is wrong or incomplete. So actually they don't contradict, but you have to fill in the blank to make it complete. The answer lies in the fact that you have to understand that S in two cases of what? S of which? The first case, it is of course the universe, isolated system, as I mentioned. That is second law. But in the second case, when Clausius inequality is being used, it is about the system. So two S refer to two different situations or conditions of system. So they otherwise it's okay, no question of confusion. Okay, so they don't contradict. Well, second law, different statements, understanding through diagram. We have so many statements of second law actually. So let us just follow this diagram. We are considering some Carnot engine or Carnot cycle like thing. So two temperatures, hot and cold, reservoir and sink. QH is absorbed by the engine TH, but no QC is there. It's not releasing any heat. So of course, from first law and the energy conservation, the QH, whole of the amount of heat absorbed, is converted into work. So minus W equal to QH. So it is all about complete conversion of heat into work. Okay. Now let us see it from a different aspect. That no sink is there, that means no TC is there. That means only a single temperature is there. Okay, no separate TC is there. So that means TH and TC can be taken as same if you consider the Carnot expression. Now in Carnot's efficiency, engine efficiency, we know that minus W by QH is defined and is explained or expressed as TH minus TC by TH. Now if TC and TH are same, this numerator is 0, so 0 by something is 0, so the whole right hand side is 0. That means W equal to 0 into QH, that is 0. That means no work. So we are getting a completely confused conclusion. One is saying there will be no work, Carnot, and the other one is our proposed engine, where complete conversion is done. So no work versus complete conversion, right? So definitely we will be interested to get complete conversion, but unfortunately this is wrong. Carnot is correct. So this is, we are getting from what? From no deduction actually. It is the second law. Of course, a separate version only, and that is Kelvin or Kelvin-Planck statement that no cyclic process is possible in which heat is taken from a hot reservoir and converted completely into work. So this itself is impossible. That is second law. Okay, Kelvin-Planck statement. Now we can think of a tricky way that okay, we'll obey Kelvin, but in a tricky way we'll disobey at the same time. So is it possible to get an anti-Planck engine? Let us see what is the trick. The trick is simply that this is the normal Carnot engine, that it absorbs and it releases some heat, and the rest of the heat is converted into work, QH minus QC. So this is what is all about Carnot engine. Now if I make an arrangement by introducing a second engine whose job is to pump the QC amount of heat from the lower temperature to the higher temperature, the same QC, that is this job. So if I now combine these two engines, so effectively you see at the lower temperature TC, QC is coming here of course, but QC is rejected by the sink. So effectively there is no change in QC, and the hot reservoir heat change is QH minus QC because it gets back QC amount of heat, and where it goes, QH minus QC, it goes to work. So that means the Planck engine, okay, or rather anti-Planck engine. So it is possible, provided if C is possible. Okay, so maybe that we are going to get an anti-Planck, provided C is working. But unfortunately, C is not possible. The C engine is not possible, and this is another version of second law, Clausius statement. What does it tell? Heat does not pass from a body at low temperature to one at high temperature without any change elsewhere. Okay, so if C is possible, then this is also possible. Okay, and if C is not possible, then P is not possible. Okay, and that is an answer to a question that is it another law? Say for example third or fourth law, this Clausius statement? No, actually Planck and Clausius, they are equivalent in that sense. C is yes, P is yes, C is no, P is no. So that is the answer to the question, that they are equivalent. Okay. So if I think of an anti-Clausius device, it doesn't exist, you know, but if I can explain in other way. So let me try. TC, TH, Q is the amount of heat transferred. So the entropy change here is minus Q by Tc and here Q by Th. So these are the surrounding entropy change at lower and higher temperature respectively. Now if I consider the total entropy change, how? Device is an engine, so it comes back to its original state, so it's a cyclic process. So of course S is a state function, so delta S for device is 0 and delta S surrounding is this plus that, delta S H and delta S C. So if I just put the expression minus Q by Tc and Q by Th, so you can take Q common, so Tc minus Th by Tc and Th. And here you see that Th is greater than Tc, right, by definition, by way we have arranged. So of course the right hand side of the last line is negative, okay. So delta S universe we are getting negative if this arrangement is supposed to hold true. But that contradicts the second law, because we know second law states that delta S universe or an isolated system must be greater than 0 for an universal change, or at best equal to 0. It cannot be negative. So the device violates the second law and we cannot get an anti-Clausius engine. That is very unfortunate. Okay. A few words on statistical entropy. This is, you know, everyone that Boltzmann, and it's written S is K log W. So third law, actually we are entering the arena of third law to some extent, not in depth. Like the first and second law, it doesn't give you any new function. Like U and S, we got it from first and second law respectively. Second point is no perpetual motion machine is impossibility of PMM is there from this third law, and it only refers to T, which we get actually from zeroth law, and S, second law. So it gives you almost nothing new, but let us see what does it give. It tells about the number one, unattainability of absolute zero. That is the one of the outcomes, and in the limiting condition delta T limit T tends to 0, S is 0, entropy itself in the limiting condition is 0. That is also another outcome of the third law of thermodynamics. Now I will again cite often done mistake that after statistical reduction we can show that ds is K d ln W, and then immediately we write K is S is K ln W, as if we are integrating and getting S is K ln W, right? But any mathematics students will object to this argument that no, if you integrate, you should get an integration constant S0. So how you can say that your S0 is 0? Is an assumption? No, actually the third law is entering here. How? Because we know that third law itself says that delta S is 0 in the limiting condition T tends to 0. Actually delta S0, not only that, S itself is 0 in that limiting condition. So this is third law. Now if I apply that limit T tends to 0 S is limit T tends to 0 K ln W plus S0. So we are applying here. Okay. Now the left hand side is 0 because of third law. Okay. 0 is left hand side third law. And in the T tends to 0 condition, all the particle of the system are in the ground level. So there is no one way of arranging all the particles, which we call thermodynamic probability, and that W is only one way of arranging, because the temperature is almost very low. So ln 1 is 0. So the second time is also 0. So 0 equal to 0 plus S0, and that's why S0 is 0. So it's not that simple integration, but some third law is there, hidden there in this statement S equal to K ln W. Okay. Well, a few questions from statistical entropy. How the statistical entropy changes when a sample of gas heated at constant volume, and why so? Just qualitative argument, not any mathematical statement. It increases because more velocity states are available as average kinetic energy increases, because you are heating it. Similarly, how statistical entropy changes when a sample of gas heated but at constant pressure, and again it is increasing because now in this case more coordinate states are available as volume increases. Okay. And another one, how the statistical entropy changes when a sample of liquid water is frozen. Okay, so it is very simple, that decreases because now less coordinate states are available as molecules get locked in crystal. Okay. So next point is convention, assumptions, and approximations. So I do remember that in class 11 student in a class asked me that, sir, physics thermodynamics and chemistry thermodynamics, are they different? And I asked why. Because he told me that, sir, they use W equal to PdV, and chemistry people use minus PdV, and so on. So I thought that convention, that is not made clear, that it's a matter of convention and nothing is wrong. But one more important point he pointed out, that, sir, if this is so, then the answers for the same problem we are going to get different answers. But that is not true. Well, so that one has to be very clear that it's a matter of convention. Well, let me demonstrate with two examples. First of one, a problem on liquid water, as simple as water. No, it's not that simple. The problem is water is vaporized 100 degree and 1.013 bar. The heat of vaporization is 40.69 kilojoules per mole, delta H. Find the values in kilojoule per mole of all four terms, W, Q, delta U, and delta H. So we can solve this problem easily, but often we forget that what are the assumptions we are taking or making. Water vapor is ideal, that is one assumption, and volume of liquid water compared to the vapor is negligible, right? So these are the two assumptions we already have made for this answer. The rest of the things are simple. W is minus P delta V, so delta V is V vapor minus V liquid. Because V liquid is negligible, so it is PV, and that is equal to RT. So minus 3.10 at a given temperature. And Q, as you know, that Q is delta H at P, and here P is constant, so Q is nothing but delta H, which is given, 40.69 unit. Well, delta U, now first law, you have got both W and Q, so just add them to get delta U, and delta H is again from definition delta U plus P delta V, because P is constant, and that is actually delta U plus RT. So if you just put here delta U, you have got RT, you calculate, and you get back 40.69, because that is supposed to be delta H is QP in the second part. Okay. So that is one example, but one more important example is taken from statistical thermodynamics. Well, follow it carefully. Consider n particle two level system, level 1 and level 2, or level head and level tail, you can say. So evaluate W1 is to 1. So out of n, suppose n is even number, so out of n number of particles, if you divide 50-50 in two levels, so what would be that W value? That means thermodynamic probability, which we call the number of ways of arranging this configuration, and the W total, and compare the results and comment. So we are going to get a very interesting conclusion. Let us see the first of all, the total number of ways of arranging the n particle in two level system, right? So it would be easy if I think that two levels in head and tail, that is now relevant to a coin toss problem. So you know that for a single coin, there are two possibilities, that either head or tail. But there are two coins if you toss, then there are four possibilities: head, 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 tail, tail, head, and tail, tail. So 2, 4, and you can easily show that if it is 3, the number of particles, then it is 8. So now by the time you have got the pattern, that 1, 2, 3, n, you get W is 2, 4, 8. That means for 4, of course, you can get that actually it is 16, and the formula is 2 to the power n. So total ln W total, all ways, I mean not 1:1, all possible ways you can take together, and that would give you 2 to the power n, or log is n ln 2. Now what is the 1:1 configuration? So we have a formula for that, factorial n by total number of particles by product of factorial ni, where ni are the number of particles in different levels. Here only two levels are there, and 50-50, so n by 2, n by 2. That's why W1:1 is n by 2 factorial by n by 2 factorial whole square. n by 2, I think something is wrong. Okay, please check it. But the important point is that W1 is to 1, you will get the answer n ln 2. So what's wrong with that? That is the answer, fine. But no, the problem is that that is equal to the n ln W total. So how W, a particular configuration which is 1 is to 1, 50-50, how it can be same, exactly same to that of the total ways of arranging, of which W1 is to 1 is only a part. That means how a part can be equal to a whole, to the whole. That's a fallacy, right? Clearly something somewhere has went wrong, and where it is thus, it is too good to be true, the result. And the thing is that you have used in this deduction some Stirling approximation. So that's why it is not an exact result. So it is slightly less than n ln 2. So there is no, finally there is no fallacy of contradiction. Okay. And the last part, so much from a single equation. RT ln Kp is minus delta G naught, or Kp is e to the power minus delta G naught by RT. So this is a very frequently occurring equation that everyone knows. But my point is that to elaborate that how one can get so many informations from a single equation. First of all, if exponential to the power something, so this something must have unitless, would be unitless, dimensionless, that you know. Now R is joules per Kelvin per mole into T, so Kelvin goes out, so joules per mole. So delta G naught must be joules per mole. Now what does it mean for a reaction? Delta G naught per mole, actually call it per mole of equation or per mole of reaction. This is the first point. The second point is Kp. What are the things that you can share with this expression Kp, about Kp? First of all, Kp is dimensionless. As you know, e to the power something is dimensionless. So Kp is dimensionless. Of course, you are taking the ideal gas system. And second point is Kp doesn't depend on P. On the right hand side, delta G standard heat change, right, gives to energy change. So by definition, it is at 1 bar. So pressure is constant. Okay, so it doesn't depend on P. Of course, it depends on temperature. And delta G is a extensive property. So delta G would also depend on the stoichiometry of the reaction and the way you are choosing your standard state, because you are calculating delta G not right, standard. So how it depends on standard state chosen. So these are the things that a single equation gives. So that is a good way of looking at any given equation, that how much information you can extract from the equation. The more you can, the more you will learn. So with this much, I would like to thank you for watching. Our next video is supposed to come as session 12, and that would be on concept booster multiple choice question. That will be our part 4 of thermodynamics series. Until then, please keep on watching. Do subscribe. Encourage your friends to subscribe and watch, and let us learn together. Thank you very much once.